Okay, this is chapter 38, and up until this point, we've talked about how light has got to be a wave. It can interfere, it can diffract, and do all that fun stuff. It's definitely a property of waves. However, now we're going to start treating light like a particle. This is going to allow us to introduce a new thing. This thing is called a photon, and that's kind of like a particle or a discrete little chunk of light. And we're going to talk about how we can have light on a photoelectric surface, and an incident photon can eject some electrons, creating a current. We'll talk about how we can do this with X-rays, how we can have Compton scattering and pair production, and we'll kind of have to reinterpret how light can diffract and interfere now that we know that we can treat light with photons like a particle. And we'll finish off by Heisenberg's uncertainty principle. So even as late as the early 1900s, we had Maxwell's equations. We knew that light behaved like a wave, and that was essentially good enough. However, the wave model theory of light broke down in several instances, and we'll talk about those. Einstein came along, and he was interested in the photoelectric effect, which is essentially if you have light incident on a surface, how can we eject light? And he created this thing called a photon, which is like a discrete unit of light, so a particle of light, if you will. And it turns out that we can actually treat light both like a particle and like a wave. And in general, we're going to treat light like a wave as it propagates, going from one location to another location. And when light is generated, or when light is incident upon a surface, then we're going to treat it like a particle. One thing that's really kind of important is we're treating these photons as having discrete units, discrete energy, and actually another word for that is quantized. And what we're kind of getting to is we're getting more to a quantum realm. So let's talk a little bit about the photoelectric effect. And the photoelectric effect essentially says if you shine light on a surface, you should be able to eject some electrons. And the wave model of light would predict that frequency does not matter, only amplitude matters. However, something that we've observed is if we illuminate a photoelectric surface with some low frequency light, electrons are not ejected. However, high frequency light does, and the wave nature of light simply does not explain this. It also, the wave nature of light would say that there may be a time delay as we start to eject electrons coming off the surface if we have to build up enough energy. So when we turn the light on, electrons may not immediately come flying off, and they do. Some other interesting things about the photoelectric effect, where the wave nature of light breaks down, is if we are shining a light onto a photoelectric surface and we're ejecting some electrons, and that's great. If we were to double the amount or double the intensity of light, then the wave nature of light would say that they're going to come off with different amounts of energy, but really more light ejects more electrons and they have the same kinetic energy. And so we're asking ourselves, what's up with this? And the last place where the wave nature of light breaks down has to do with this thing called stopping potential. So if we were to have some light incident upon a photoelectric surface, then if we put a voltage source between an anode and the cathode, then the electrons are going to essentially be attracted to the anode. We should be able to measure that current. However, if we were to go ahead and have the same setup and reverse the battery, as you can see right over there, then actually the electrons that get knocked off are going to be repelled. And the amount of voltage that it takes to essentially make them go back to the surface is what's called the stopping potential, so it's stopping those electrons. And what the wave nature of light would say is that as we increase the intensity, then the stopping potential should also increase. However, what we found is that is not the case. So what Einstein did is he said, okay, well, light is going to come in as these particles called photons, and these guys are going to have some energy, and actually the energy that it has is going to be related to some constant, which is called Planck's constant, multiplied by frequency. And so the frequency of the photon, of the light, is going to be related to how much energy it has, and you can see this is a discrete or quantized amount. This guy right over here is a constant, and I'll talk about what that is in just a little bit. And what's happening is the light's coming in, and in order for us to knock an electron off of, in this case, some cesium, then it has to absorb a photon that has enough energy to ionize or knock out one of the outermost electrons of the photoelectric surface. And essentially, a blue photon does not have enough, or has enough energy, but a red photon does not, because the frequency of the red photon is lower than the frequency of the blue photon. So here's a little Java simulation on the photoelectric effect, and what I'm going to do is I'm just going to shine this light on that surface, and you can see that instantaneously electrons start coming off of this guy. And as I start to go up to closer to red, then I'm going to hit some point where the frequency is too low, the wavelength is too high, and I'm not going to have enough energy to knock electrons off of this surface. And it doesn't matter how intense it doesn't matter how intense I make that light, I still can't eject electrons from that surface. I have to go down in frequency until I can go ahead and knock these guys off. And I can accelerate them by putting a voltage right over there. And actually I could try to measure the stopping potential by turning the battery around and get this guy right over here. Now, some things to kind of keep in mind are different materials are going to require different energies. It's going to switch from sodium to zinc, and you can kind of see that a wavelength that worked for sodium is not going to work for zinc, and I'm going to need to go lower and lower and lower until I can finally start to eject some electrons off of this surface. So different surfaces are going to require different amounts of work in order to eject electrons. So kind of coming back to this guy right over there, we know that to eject electrons we're going to have to do some work, and the amount of work is actually going to be the charge of an electron multiplied by the stopping potential. And actually, if all that work could go into kinetic energy, then we could say that the charge of an electron multiplied by the stopping potential is going to be equal to the kinetic energy gained by the electrons. So these things called photons, which are kind of like particles of light, contain very discrete amounts of energy, and I gave this to you on the last slide. I'll give it to you again because it's really super important. The amount of energy they have is going to depend on essentially their frequency and Planck's constant. And kind of the idea of a photon is an extension of some of Max Planck's work a couple years before Einstein, and we'll talk about that actually in chapter 39. So this little h guy right over there is going to be Planck's constant, and it's going to be 6.626 times 10 to the minus 34 joules multiplied by seconds. You will also see this occasionally written in electron volts, because we are going to work in electron volts quite a bit. So definitely want to make sure you have those guys. And photons are also going to have some momentum, and how much momentum is going to be related to Planck's constant and the wavelength. So these photons have some particle-like properties and some wave-like properties as well. Photons will definitely have a wavelength and a frequency, and we can relate the speed to the frequency and the wavelength as such. And so occasionally you'll see the energy relationship written as such, where we've just kind of swapped out the frequency for the speed of light and the wavelength. So what this kind of does is it explains how we can have some frequencies that have some energy that can knock electrons off of the surface, but other frequencies cannot. So the frequency really matters when it comes to the energy. Now, how much energy would an electron have when it comes off of the material? Well, that's going to be related to how much energy the photon had, as well as this guy right over there, which is a phi, and that is the work function of the material. And different materials are going to have different work functions. And actually, if we were to say, well, what is the maximum kinetic energy that an electron would have, then it's just going to be related to how much energy the photon had minus the work function of the material. Now, I do want to talk a little bit more about the work function, but before I do that, I do want to remind you about the electromagnetic spectrum, and here we have it with increasing frequency, kind of working our way through radio waves and microwaves up through visible light, and then through X-rays, and then all the way up to gamma rays. And keep in mind that as the frequency is going up in this direction, that the energy is also going up in this direction. And even if we were to look at our typical Roy G. Biv, here we have increasing wavelength, or decreasing wavelength because frequency is increasing, and so as we work our way up in this direction right over there, we're increasing the frequency. And this kind of explains why we can get sunburn from ultraviolet light, there's more energy, and not from infrared light. So really quick, let's take a look at two examples, 38.1 and 38.2. So if we have a laser pointer and we know that it puts out 5 milliwatts, and that would be equal to the power of the laser, and the wavelength is going to be kind of red, about 650 nanometers. Let's figure out what the momentum of one photon ought to be. So we're going to say the momentum is going to be equal to h divided by lambda, where we're going to use the joule version of this, 6.626 times 10 to the minus 34, divided by 6.50 times 10 to the minus 7th meters, and the momentum of one photon is going to be 1.02 times 10 to the negative 27, with a unit of kilogram meter per second still. And this is really tiny. It's a very small momentum. If we wanted to say, well, how much energy does just one photon from this laser pointer have, we could say that's going to be equal to the momentum multiplied by c, and so that's going to be 1.02 times 10 to the negative 27th multiplied by the speed of light, 3 times 10 to the 8th meters per second, and the energy of one photon is going to be 3.06 times 10 to the negative 19th joules. And you can see this is a really small number, so very often it's convenient to express this in electron volts, which is going to be 1.91 eV. So now, really quick, let's take a look at example 38.2. If we had a photoelectric surface, and we found that we reversed the potential, and it took 1.25 volts in order to reduce the current to 0, that's going to tell us that this is going to be the stopping potential. And what is the maximum kinetic energy that we could get off of this surface? Well, the kinetic energy is maximum kinetic energy is simply going to be equal to the charge of one electron multiplied by the stopping potential, and actually this is going to work itself out to be 1.25 eV. We could of course convert this to joules and figure out how fast this guy would go, how fast the electrons would move, and we could say that the kinetic energy is going to be equal to 1/2 mass speed squared. Something I did forget to mention is we do have different surfaces. All these guys are metal, and they're going to have different work functions, which is just kind of an intrinsic property of the metal.